Okay, so this is the second video in chapter 23 on geometric optics. In this video we look at curved mirrors and the kinds of images that are created with these things. One kind of curved mirror is the spherical mirror. This is shaped like a section of a sphere. These can be reflective either on the inside, which we would call concave mirrors, or they'd be reflective on the outside, which we would call, of course, convex. Now, these mirrors can create a variety of different images. So whereas plane mirrors could only create images that were the same size, that were virtual, and they were sort of like flipped right to left, sort of like the right hand becomes the left hand kind of thing. Plane mirrors are somewhat limited in their application. They're really good for viewing our image if we're getting ourselves ready for the day, but there's a lot more practical applications for curved mirrors, and that's because of the different kinds of images that can be created. So either enlarged or reduced, they could be upright or inverted, or they could be real or virtual. So where the object is located relative to the center of curvature really determines these image properties. And so here you can see this this penguin that's in front of this curved mirror. It looks like we have sort of an enlarged image of the penguin here, and for this one over here, it looks like we have sort of an inverted image, and it actually looks to be reduced in size. So why do these images look the way that they do? All of it really depends on how close these things are to the curvature, the center curvature of that mirror. Let's see if we can figure out how we can use the law of reflection to sort of predict the location of those images. First, these are called real images. Where the light rays actually converge to a point would be called a real image. And so here I have maybe a light bulb out in front of this this spherical mirror, and we have a couple of light rays that are incident upon the mirror at various locations, and we can see that those light rays are going to converge upon a point. In this case here, that convergence is sort of on the same side as the object. And it looks like it's creating an image that is upside down or inverted. And in this case, it actually looks like it's reduced in size. If you recall that the virtual images of a plane mirror were on the other side of the mirror back here, these real images are on the same side as the object is. Okay, and so over here we can see that this is sort of an image of some light source. Maybe it looks like it's a light bulb of some sort. Over here, this mirror is sort of creating a real image that's projected onto the screen. So light emanating from the bulb strikes the concave mirror and reflects according to the law of reflection. Only two rays are shown. They intersect or converge in front of the mirror, making the image real. This kind of image can be projected onto a screen. Okay, let's see if we can't use some ray diagrams to understand where those images are created. So first we'll take a look at a couple of aberrations due to spherical mirrors. So parallel rays striking a spherical mirror do not all converge at exactly the same place. If the curvature of the mirror is large, this is called a spherical aberration, and so we would need to use parabolic reflectors. It's very expensive. If you remember the video that we watched on the Hubble telescope, we watched that previously in the year that I'm creating this video. If you haven't seen that video yet, perhaps we'll show it at some point during the school year. But the Hubble telescope suffered from a little bit of aberration. They of course knew to make it a parabolic reflector. They just did not polish the surface correctly in order to get a nice clear focused image. So if we have just a plain spherical mirror, we would see that we could have some sort of aberration just due to the fact that they don't all converge at this particular point. So if the mirror is large, then we would have somewhat of a spherical aberration. If the mirror is a little bit smaller, then we can get a pretty good approximation, a pretty good image created from small spherical mirrors. Otherwise, we'd have to use a parabolic mirror, which can be somewhat expensive to create. If the curvature is small, the focus is much more precise. The focal point is where the rays parallel to the principal axis converge. So we often consider parallel light rays, and where those would converge would be called the focal point for that mirror. So using geometry, we find that the focal length is half the radius of curvature. So we could write that as f. The focal length would be half the radius of curvature. So f is equal to r over 2. We'll see that equation come up in subsequent applications here. Let's go ahead and see if we can't use what's called ray tracing to figure out where an image is located for an object. So whenever we do ray diagrams, we often draw 2 to 3 different primary rays in order to see where the image would be created. So the first ray would be a ray that's parallel to the axis, and after it reflects off the mirror, it would pass through the focal point. So if I were to draw that here sort of freehand, let's consider I have some object way over here. Let's draw it right here. Often we use an arrow as sort of a length and an orientation to it. And so let's say that I have a ray of light. Let's make it a little bit smaller since it looks like it's bigger than my mirror over here. Let's go ahead and draw it right here, make it about that size. And so they have a ray of light that comes off here. It's parallel to the principal axis. And oftentimes, I know it might be hitting the mirror here. Oftentimes we just sort of extend it to go back to the back side of this mirror so that we can use basic geometry to be able to do this. If this is the center of curvature of that mirror over here, we would say that the focal point would be half of that length, and so this would then go right through the focal point of that mirror. Okay, and so it would continue on like so. Okay, so that'd be ray number 1. Now ray number 2, let's use a different color here. Ray number 2 is a ray that goes through the focal point, and after it reflects, it would reflect parallel to the principal axis. So let's go ahead and use, let's see, I got red here, same color as that object. Let's change this to blue. There we go. So this one's going to go through the focal point. See if I did that well. Okay, not too bad. Then it continues on, sort of in a straight nature, and sure enough, when it hits there, it reflects, and it reflects parallel to the principal axis, and so that would go back this way. Okay, and these two things sort of converge upon that point. Let's do one more here. Let's go ahead and draw this one as pink here. So let's draw a ray that is perpendicular to the mirror, reflects back onto itself. Okay, so if we were to draw that perpendicular to the mirror, it would actually have to go through the center of curvature here, and so it would end up having to go through here. And so if this thing were drawn and that were the center of this portion of the sphere, it would hit this mirror at this point and go right back, reflect right back onto itself, and sure enough, you can see that all three of those sort of converge on the same spot. And so this is, of course, where the image of this pencil would be located. So it'd be located right here. You notice that since I drew I projected the 3 rays from the tip of this arrow, that tip would be sort of down here, so that image would be inverted. You can certainly see that the size of that arrow is smaller, so it would be an inverted image. It would be reduced in size. In this case, it looks like it'd be located somewhere between the center of curvature and the focal length. Okay, so somewhere in that area. So this is how we might use ray diagrams to sort of predict the location of the image formed by a concave mirror. Now, in reality, we have 7 cases for mirrors. Okay, and so one of those cases that I just showed you, I think it was like case 3 or 4. I can't quite remember what that number is, but let me go through these with you really quickly. So this is, again, just freehand drawings to show you the 7 cases of mirrors. So case number 1 would be when the object is at infinity away. So it's really, really far away, and what that means is that the light rays are coming in, and since all the light rays are coming in, they would end up being parallel to the principal axis. Right? Since the object is so super far away, every one of these things would then just go right through the focal point. By definition, the focal point is the location that parallel light rays would focus. This would be case number 1, where the image is a point image that would be located at the focal point. So if I wanted to take the light from the sun and focus it onto a point and maybe burn a hole in a sheet of paper or something along those lines, I would use a mirror like this and place the paper right there at the focal point. And so all of that sunlight would then be intensified and focused at that point. You could burn a hole in that sheet of paper. So that'd be case number one. Case number two is where an object is outside the center of curvature. So let's go ahead and draw that out here somewhere. And so it looks like actually the example that I gave you here was case number 2, where it was outside the center of curvature. We are already seen that that would create an image that is sort of in between the center of curvature and the focal point. So that would be where the image is created for case number 2, where it's outside the center of curvature. Now case number 3, and again these cases are really useful to memorize so that you don't have to draw ray diagrams all the time to try to figure out where these things are. Case number 3 is where the object is actually located at the center of curvature. Okay, and so that would be at that particular spot. I might have the first ray that I go to draw would be something that looks like this, goes through the focal point, and then the one that is going through the focal point would sort of reflect and come back, and it would actually, if I did this correctly, it should actually come back and create an image right at the center of curvature. So I'd end up getting an image exactly at the same spot as the object. It would be the exact same size, and it would be inverted. And so it's almost like this is almost like a plane mirror creating the exact same kind of image, except it's no longer virtual. It's over on this side. It's actually a real image. It's inverted, and it's at the exact same spot as the object is. There's some pretty cool effects that we can create here. As a matter of fact, if you haven't seen these yet in our classroom, I'll show you an example of exactly case number 3, where we can create some pretty cool optical illusions. Okay, and so let's take a look at case number 4. So case number 4 here, so switching the color scheme. Let's see if I can't go back to blue. There we go. Case number 4 would now be when I'm inside of the center of curvature, but outside of F. So let's go ahead and draw one right here. So this might be our object. So we've moved it inside the center of curvature. Let's draw some of these rays here. So here we have this one coming in, hits the back side of that mirror, goes through F. And then of course we have one that goes through F, and that comes down here. And when it hits this back side, it reflects and it comes way back this way. And sure enough, these things are going to coincide back here. Well, it's pretty tough to draw the one going through the center of curvature. We might look at this and say, well, that's going to go over here, and then it's going to come back, and it's going to go this way, and then come right back onto itself. And if I drew this correctly, it would end up coming back to the exact same spot. What we get is a real image that is enlarged in size, bigger than this. It's located further than the center of curvature away, and it's located back here. So this would be case number 4, where I get sort of an enlarged real image that's further than the center of curvature away. Okay, applications of this might be, I don't know, could be something that we're trying to project onto a big screen, maybe in a movie theater or something along those lines, where I want to be able to have a bigger image than just maybe the film that's maybe going through the projector, something along those lines. Okay, let's take a look at case number 5 here. So case number 5, maybe you've recognized the pattern. We started from infinitely far away, coming into outside of C, and then we're at C. Now we're inside of C, but outside of F. Where do you think case number 5 would be? In case number 5, you've guessed it, would be right at the focal point. So if I place an object at the focal point of this mirror, what we'll see is that this is sort of like the opposite of case number 1, where I have these light rays are going to come out. It's going to come through here, and let's see, it's sort of hard to draw these other ones. These light rays will now come out parallel from here. They'll never converge. Okay, so this is sort of like the opposite of case number 1, where these light rays now are coming out sort of parallel from this. Okay, and so this would be case number 5. Perhaps a good application of this. Maybe I'll put a light bulb here light bulb that I might be putting in front of my spherical or parabolic reflectors of my headlamps, on my car. And sure enough, all of that light that's striking here will now come out parallel from here and maybe go out in front of my car and sort of illuminate the roadway for me. So case number 5 might be an example like that. Case number 6, now you notice that we are inside of the focal point. Okay, so we're inside here. We're going to place some object inside here. And if we go to try to draw these rays now, let's see, we would have a ray that is maybe parallel, and that parallel ray again goes through F. Okay, so it's the same 3 rays that we try to draw. Now this one here is a little bit harder to draw. It's the one that goes through F. When it hits this mirror here, it sort of reflects parallel. And I know you might look at that and say, well, it actually never hits the mirror. So we're just sort of using these geometric drawings here to try to figure out where that image would be located. So even though it looks like it goes beyond that mirror, certainly this is just to help us visualize where the image is located. Now these 2 rays on this side are diverging. These 2 rays will never meet, right? So this one's going off sort of off to the like 7 o'clock or 8 o'clock area, and this one's going off to the 9 o'clock. These things will never actually meet over here, but they do appear to be coming from a point behind the mirror. And so this point back here is where this is the image appears to be behind this mirror. This would be the image of that object. You notice that it is enlarged and upright. It's also virtual. It doesn't actually exist. Okay, and so this would be the example. Let's go back to here for a second. That would be this example here where I had this thing relatively close to the mirror, and I've got a nice enlarged image of that penguin. And so boy, a good application of this might be a shaving mirror or a makeup mirror, where I need sort of an enlarged image of my face or something else for me to be able to see more detail. And so that would be a good application of case number 6. Okay, and now case number 7 is for, let's see, if these are all concave mirrors, case number 7 would be a convex mirror. All the images created on convex mirrors are the same kind of image, whereas I might have 6 different cases dealing with concave mirrors. I really only have 1 case for the convex mirror, and so this is a little bit harder to draw. Let's see if we can't go ahead and do this here. I still have some parallel rays, so here's a parallel ray to the principal axis. Now, since as a mirror it sort of reflects, it's going to reflect at an angle that makes it appear to be coming from the focal point, right? So from behind here. So it's going to reflect this way, seeming as though it came from here. Okay, so it looks like that. Now, these other ones are a little bit tougher to draw. If you remember the one that was going to go through F, I'm going to go ahead and draw that here. It looks like it's on its way to go through F, right? It looks like it's going to go through F, but when it hits that mirror, it reflects parallel to the principal axis. And so I'll draw some arrowheads on here to show which way these things are traveling. Okay. These 2, again, are diverging. These 2 light rays will never meet over here, but they do appear to be coming from a point behind the mirror, and they appear to be coming from here. Now, this image is also virtual. You notice it's behind the mirror. It's also upright, but you notice it's smaller than this one here. Okay, so this would be case number 7. It's for a convex mirror. A good application of this might be something to prevent shoplifting, or maybe to discourage it, right? So this might be one of those mirrors that you see that they place in the corner of a convenience store or something along those lines. It provides a really good view of the entire area. Of course, what we're sacrificing here is size, right? So we can't really see the objects all appear, or the images all appear to be quite a bit smaller than the actual object, but it does give us an enlarged viewing area. Okay, so there's applications for all of these things, and so curved mirrors have a lot of application based on where we locate that object in relation to the center of curvature. Okay, and let's see. Here we're going to start looking at the using some equations, not just the drawings, to predict the location, but it's actually some mirror equation. So geometrically, we can derive an equation that relates the object distance, the image distance, and the focal length of the mirror. And your book, I think, goes through the derivation of that. And so I'm going to save that for your book. I just want to show you what the equation looks like. 1 over do plus 1 over di is equal to 1 over f. Again, these things here would be helpful for you to know. Do is the object distance. So where the object is in relation to the mirror. Di, of course, would be the image distance. And the focal point, focal length would be, well, we remember that as being half the radius of curvature. Okay, so this would be, f would be the focal length. Okay, and so we can also find the magnification, which would be the ratio of the height to the object height. So if we want to look at how big the object is in relation to the image, or how big the image is in relation to the object, we could just compare the two. So we could say hi over ho, this would be the height of the image, this would be the height of the object. Through geometry, you would see that it's actually equal to the negative of the ratio of the image distance to the object distance. So a nice little convenient way of determining the magnification of that particular mirror. Probably easiest to do this by looking at a few examples. Problem solving, draw a ray diagram, see where the rays intersect, or just simply memorize those cases. And that's what I would encourage you to do, since drawing those ray diagrams every single time would get a little bit time consuming. Apply the mirror and magnification equations. Sign conventions have to be considered here. If the object, image, or focal point is on the reflective side of the mirror, its distance would be positive and negative otherwise. Magnification is positive if the image is upright, negative otherwise. Check that your solution agrees with the ray diagram or with your memorized cases. Let's go ahead and take a look at a few examples here. Okay, so a concave shaving mirror has a focal length of 33 centimeters. I'm going to go ahead and make a little list here of some things that I know as I read this. So the focal length, it's a concave mirror, so f for this would be 33 centimeters. I'm going to go ahead and keep everything in centimeters here. Now it's a concave mirror, so it'd be something that looks like this, and the focal length is on this side, so here would be the center of curvature, here would be the focal length. You notice that since this is on the reflective side of the mirror, that this would be a positive value. Okay, calculate the image of position of a cologne bottle that's placed 93 centimeters in front of the mirror. Okay, so if this is 33 and this is 66, then we're out here in case number 2. So we're out here somewhere. Okay, so this is where the cologne bottle is. In its distance, let's see, this would be d to the object is equal to 93 centimeters. So again, that's on the reflective side of the mirror. That would be a positive object distance. Okay, and it says calculate the image position. So where is the image located? We should remember that it's going to be somewhere in between C and F, right? Because I sort of went through and did this quickly in my head. I'm thinking, okay, here's a ray of light, comes in through here. Here's a ray of light, hits here, comes back through here, and I could draw this one if I wanted to. And sure enough, it's going to come in here somewhere. I just want to figure out exactly where it is without having to draw the diagram to scale. So I know it's going to be between C and F. It should have a positive image distance somewhere greater than 33, less than 66. So my diagram is going to help to make sure that I've done my math correctly. Okay, and then we're going to calculate the magnification of the image and determine if the image is real or virtual. We know that it's going to be real here because it's on this side of the mirror. And we drew the ray diagram. So let's go ahead and just do the math here. So 1 over di plus 1 over do is equal to 1 over f. I'm looking for di, so let's go ahead and solve that by subtracting 1 over do from both sides. And let's go ahead and start to plug in some numbers now. 1 over the focal length is 33 centimeters minus 1 over the object distance is 93 centimeters, and so 1 over di is equal to, I'm going to pause the video here for a second. Okay, I'm getting that 1 over di is equal to 0.01955, and that would be inverse centimeters. So when I take the reciprocal of that, I get that di will be equal to 51 centimeters. Okay, there's 51 and some change, but let's go ahead and just round that to 2 digits there. So the image distance, 51 centimeters. Sure enough, I see that that's between 33 and 66, which is what I was expecting, and so that's good. And let's see, is the determine the magnification. Well, magnification we said was negative di over do, and so let's see, the image distance would be negative, and that'd be 51 centimeters over do was 93 centimeters. And so when I take that one divided by 93, I see the magnification is a negative 0.55. And so that would give me the relative size of the image. So it'd be about 55% of the height of the cologne bottle. It would be inverted, which is what that negative sign means. Okay, so there we go. A little problem there with the mirror equation. Let's try this one over here. A concave mirror is designed so that a person 25 centimeters in front of it sees an upright image at a distance of 50 centimeters behind the mirror. What is the radius of curvature of the mirror, and what is the magnification of the image? Is the image real or virtual? So this is a concave mirror. Okay, and so let's see, something that looks like this. Principal axis. The concave mirror is designed so that a person 25 centimeters in front of it, that might be like their eye, right, that they're looking at, or something along those lines. So they're at a distance of 25 centimeters. So this would be the image, or the object distance rather, do is equal to a positive 25 centimeters. Again, it's on the reflective side of the mirror. It's designed to see an upright image of a distance 50 centimeters behind the mirror. So what they're going to see here is they're going to see sort of an enlarged image back here, and it's going to be bigger. And so they might be looking at this and they see an enlarged virtual image. This is going to end up being virtual. It's on that side of the mirror. And we notice that its image distance, di, is equal to, let's see, 50 centimeters behind, but we have to put that negative in there because it's behind the mirror. Okay, so di would be a negative 50 because it's on the other side of the reflective surface. And let's see, it's asking for what is the radius of curvature. Well, we do know that, let's see, we said f was equal to r over 2, so r would be equal to 2f. Whatever the focal length is, we'll see that the radius of curvature is twice that. Okay, so let's go ahead and figure out what the focal length is. So let's say 1 over f. I'm going to write that as 1 over di plus 1 over do. And so 1 over di. Well, that'd be a negative 50 centimeters plus a 1 over 25. Now this would be a positive over here, okay, for that. And so let's see, 1 over f. I'm going to pause this video again and do that math quick. Okay, and I'm getting that f is equal to the reciprocal of 1 over 0.02, which would be 50 centimeters. So the focal length of that mirror would be 50 centimeters. Now notice it is positive. Since it's a concave mirror, I would expect a positive focal length, but I am inside of the focal length. So if the focal length is over here, I'm located inside of it. That's why I'm getting an enlarged virtual image. Let's see, so that looks good. What is the radius of curvature? R then would be equal to twice that, so R would be 100 centimeters. So I would have a radius of curvature for that mirror of about 1 meter. What is the magnification of the image? Well, let's see if we can go ahead and do that. Magnification again is negative di over do, and in this case we have a negative. Di is a negative 50. do was a positive 25, and so we get the two negatives reduced, which is what we'd expect. It's an upright image there, and so we get a magnification of 2. So that image would be twice as big as the object. So there we go, a few examples of how we might use ray tracing and also the mirror equation to look at concave and convex mirrors. What kinds of images, the image properties and so forth, all of that for curved mirrors.